on decades ago that 5G and millimeter wave would someday happen for the mobile industry. I'll take a quick look through the history books of some of the key works we did that eventually convinced the world that indeed we could move up higher in frequency for the mobile industry and Wi-Fi as well. And then I want to share with you the amazing growth of the cellular telephone industry, and then share some very new results which show why there will be a data explosion unlike we've ever seen in the history of the world, all coming to our handset. So first, just very briefly, what I do at NYU is I'm one of many faculty members in a research center called NYU Wireless. NYU Wireless is funded primarily by international companies that trust us to fund students and to do fundamental research that could benefit all of the industries around the world in the wireless ecosystem. In fact, NYU Wireless is probably the largest center of its kind where pre-competitive research is funded by an international consortium of companies. And I'm pleased to say that just in the last couple of years, we've had many companies join us from Asia, such as MediaTek and Sharp. Sony is a member. A number of Japanese companies are funding our students and getting involved with the research at NYU Wireless. And you can see we do things going around this slide from the 11 o'clock position all the way around clockwise. We do channel sounding. We measure the channel and put that information into statistical channel models like NYU Sim that we make available for free on our website for the world. We do position location, new work in that based on these wide bandwidth channels. We're building a ray tracer, which we'll make available in the future. And we're building phased arrays and channel sounding equipment, as well as basic measurement science. But I'm just one faculty member. There are 15 faculty members, each working on different aspects of wireless at NYU Wireless. Now, this graphic you're probably all familiar with, and you probably know that the entire cellular industry for the fourth generations, starting with Japanese analog mobile phone back in the 1970s, all operated in the microwave band, 450 to 900, more recently several gigahertz. But it's only in the last few years that the world has really moved to millimeter wave mobile in the US, Japan, Korea, China, elsewhere. Spectrum's been opened up in the millimeter wave region. And as I'll show, that's the tip of the iceberg for the impending data explosion. We've been working in the sub-terahertz and terahertz wave frequencies up at 140 gigahertz, going up to several hundred gigahertz, where I'll show you in a minute some amazing results that show the radio channels are not that much different than everything we've done in the first 4 generations below 6 gigahertz. Now, millimeter waves, 4 orders of magnitude from ultraviolet, X-ray, and gamma rays, which are known to be ionizing radiation. NASA and other space agencies know that galactic radiation up at ultraviolet, X-ray, gamma ray are dangerous and can cause mutations to cellular and molecular biology and can cause uncontrolled growth. Microwave is 4 orders of magnitude below these radioactive particles, these high energy particles that can break ion valence shells. When we move up to terahertz, we're starting to get within 3 orders of magnitude, which makes us wonder, will it be safe as we go above millimeter wave into sub-terahertz? In 2015, a number of us wrote a paper called Safe for Generations to Come, where we looked at all the research literature in the world and found up to 80 gigahertz carrier frequency. There was no known effect, health effect, other than burning. RF burns, radio frequency burns, are known to be dangerous. But the question is, as we move up to these frequencies over the next decade or two, what are the health effects? So I hope that the global research complex will start looking into, with good peer-reviewed research, what happens up at these frequencies as we start to get within a few orders of magnitude, just 2 or 3 orders of magnitude, to the wavelengths where ionizing radiation occurs. Well, the FCC had never had any rules about going up above 100 gigahertz until 2 years ago. When they opened up the spectrum, we had been working with them at NYU Wireless, and they finally realized this may come. It may be an evolution, because millimeter wave basically was the first time we went up an order of magnitude in carrier frequency. So it's really what I call the start of the equivalent of Moore's law coming to wireless. The bandwidths and carrier frequencies will start increasing vastly compared to where they've been, just like Moore's law unleashed the computer revolution and allowed much greater clock speeds and memory sizes. I think the same will happen. And in the US, there are 4 unlicensed bands just made available, like for Wi-Fi or for applications in home or business, sensing. You can do this now today, unlicensed. There are rules for that. And in England, there are 3 bands very similar. What can you do when you get above 100 gigahertz? Well, I'm going to show you shortly. You can do cellular, telephone, mobile communications, just like sub 6 gigahertz. And if one thing's a surprise for you, I hope it's that the channels are not that different. They're not that different. The radio propagation path loss is not that different, all the way up to 900 gigahertz. So we're just starting our ascent to much higher carrier frequency. The second thing I hope to surprise you with is the amazing applications and the power efficiency we get as we go up higher in frequency. So unlike conventional wisdom that the channel is lossy and things consume more power, I'll show you it's much less power and the channels are not that lossy. The amazing applications include robotic control, fleet control, basically human surrogate. I just had the Brooklyn 6G Summit. It's on the IEEE TV. I suggest you look at it. We had some of the world leaders in business, many from Japan, world leaders from academia. It's all, the lectures are on IEEE TV, the Brooklyn 6G Summit. And I had a fireside chat with Ray Ozzie. We talked about the idea of having a human surrogate. Ray Ozzie is a very famous computer scientist, and we talked about how this wide bandwidth and carrier frequencies will allow things like a human surrogate that will do things in the cloud and also with robotics, allowing robots to basically do a lot of human level real-time computation. I'll show that in a minute. But we can do sensing at these frequencies and spectroscopy that we never could do before, gesturing, of course, and 3D video, total immersion imaging. We'll be able to use the great bandwidth and the great carrier frequencies and the wide range of frequencies to do things like image creation, see in the dark cameras, and of course, communications with massive data rates. And some of the work we've been doing shows amazing centimeter level positioning with only one base station with real-time computation. Lots of applications will come. So I thought it might be fun for this as a keynote to kick off this major conference with a look at some of the key papers that caused me to believe and to eventually convince the world that we could go up to these higher frequencies, that we can make mobile and fixed wireless and new applications work at frequencies that people never thought possible. Over 20 years ago, I was working at millimeter wave, and this is a paper we published in March of 2000, where I was working with some colleagues, and we were looking at 38 gigahertz point to multi-point with the idea of doing wireless backhaul. And this was an amazing result we found in this paper. When it started to rain, we saw that the multipath component fluctuated by about 6 dB with a little bit of increase in rain and that rain caused a lot of reflection. This was a surprise to us. 6 dB just due to rain bouncing off of the ground. This gave us some ideas, and we decided to look at a partial line of sight. In other words, a little non-line of sight. And a hailstorm came. And during the hailstorm, we were amazed that we were able to keep a radio link. And while the hail attenuated the link during the hailstorm, because of the attenuation by several dB, 20 dB, we were still able to have energy received better than we thought would be theoretical. In other words, the channels seem to be a little bit better and offer a little bit more multipath than what everyone had thought up to that point. I mean, no one had really reported fluctuating multipath in a channel or partial non-line of sight in a hailstorm. And the fact that the channel changed made me realize back before the turn of the century that someday when electronics got cheaper and our smart antennas became smaller because of the higher wavelength, and I had just written a book on smart antennas a few years earlier, so I was thinking about these adaptive phased arrays. It was clear to me then that someday we would be able to create mobile communications at much higher frequencies. And then about a year later, in 1999, we published this a few years later, we saw the spatial diversity and the impact of the channel when you use horn antennas, very directional antennas, can capture energy far beyond what people thought were possible in the day. So this was very encouraging that we could go up to millimeter wave frequencies at a time when you couldn't even make the electronics cheaply. And so in 2011, I had been giving lectures for a few years that the pending data explosion would happen. And we published this paper in 2011. About the same time, colleagues at Samsung published a paper. We were really the same time looking at millimeter wave. In fact, Samsung funded my early work when I was starting to do this in Texas. And we made the argument for mobile communications up at millimeter wave back about, well, it was over 10 years ago. Now, in 2013, we published this paper when I was at UT Austin, when I had measured the campus and was amazed to find radio signal strength going around corners, bouncing off signs and lampposts, even much better than I had ever thought. So while I had the idea back in the 1990s, it wasn't until about 2008, 2009, I started to get serious about it. And then we measured 2011, we measured the UT Austin campus and found out that energy really can reflect and do amazingly well in an urban environment. Now, I want to point out something why NYU Wireless has this industrial affiliate program and why many companies join. When you wait for research to come out in journal papers, it often takes 2 or 3 years. Even today, the best journals often take 6 to 9 months to publish a result. Our industrial affiliates learn about things immediately when they happen through lectures, through pre-publications. So companies who want to see what's happening and not wait for the publications to come out generally join these kind of consortia. Well, we published these results, and right after that, when I started presenting the measurements and moved to NYU, people didn't believe me. They thought I was really crazy. They thought the results were either made up or you can't go around corners. Millimeter wave, the wavelengths are so small, they're millimeter waves. How can they actually provide communication? And we presented the data from the UT campus with towers on top of the buildings and going behind buildings. And sure enough, when I came to NYU in New York City, a bunch of undergraduates and a really good PhD student from UT Austin who came with me to NYU, we measured the streets of Manhattan and proved to the world that not only in Texas, but in downtown New York City, you indeed can make very good wireless communication links going up to millimeter wave frequencies. Now, what happened is the world started to come to NYU. We started the Brooklyn 5G Summit. Some of you in this audience have been to the Brooklyn 5G Summit. We had great support from NTT at the very highest levels. And it was just, people started to come and see our results, and then they went to Tokyo, and they went to Shanghai, and they went to Helsinki, and they went all over the world and replicated many times our channel measurement system, and they got the same results, which was the channel's not that bad. And Intel and Nokia and Qualcomm and so many companies came to Brooklyn at the Brooklyn 5G Summit in 2018 and said, wow, this works. The other thing that I've learned a lot about is that people are worried about consumption of the power. And this is a theory we developed right before, we developed this in 2011, published it in 2014. And what we found is we developed a theory, this is a new theory, it's a very powerful mathematical framework for analyzing power consumption in any cascaded network, whether it's a circuit, a device, a radio link, a repeater system, a chip, a handset. This is a quantifiable way to measure power efficiency, and we call it the consumption factor theory. It basically creates a mathematical structure just the way noise figure and noise factor were developed for noise. It allows us to take any system and consider the power consumed by any device as the power that goes along to the next cascaded item, the power that's consumed for providing that power, and then ancillary power that's not used at all for communication. If you can break the power down into these three orthogonal power components, it turns out you have a very elegant theory to measure and compare power efficiency of any circuit, any communication system, any cascaded network. And so non-signal path devices would be, for example, the GUI or the display on a cell phone, whereas signal path devices might be the modulator, the amplifier, and the antenna. And so if you break the power consumed by any device in a cascade, it turns out you can very elegantly analyze any power consumption of any network. In fact, if you look at equation 35, this H, the power efficiency factor, if you look at this, this is a reciprocal. If you put the 1 over H, this looks just like noise figure. This is how you compute the total noise contributed by a cascaded system, except now instead of noise, it's power. So this is a very elegant way to determine the power efficiency and analyze and compare any design, any architecture, small cell networks, large scale networks, repeaters, satellites, chips, the design of a cell phone. Very powerful theory, hasn't been really discovered yet, and we're starting to use it at NYU Wireless. The basic theory is that you can develop a framework for the future energy efficient devices. We did this back about 10 years ago and proved how wider bandwidth directional antenna systems will be so much more power efficient than the first 4 generations of cellular in total power consumption. And for a future greener world, this is very important. In fact, the theory showed, and you have mathematical results, how the unprecedented data rates will occur as we go higher and higher in carrier frequency. And this is before the world even knew or believed in millimeter wave. Now, I told you it's being used now. Nokia is using this to analyze emergency high altitude platform stations, which you fly up in the case of an emergency to provide cellular from above the ground. The consumption factor theory proved that it's more power efficient and spectrally efficient to use a repeater than to put up a base station. The power consumption and the cost per bit and the overall performance is better using a repeater within certain distances than other distances. So if you're within, say, 20 or 25 kilometers, a repeater is better. Further out, you use a true base station up in the air. Interesting things like that can now be analyzed analytically. And then, of course, in 2019, we had already shown the FCC that we can move well above 100 gigahertz. And we wrote this landmark paper, which is now being used around the world. A lot of governments are looking at this document as kind of the founding document for some of the fundamental issues, the technical challenges, and the amazing opportunities we have going above 100 gigahertz. So a lot of our work that we used to convince the FCC went into this paper. Well, with that as a backdrop, I want to share some pretty exciting stuff about where wireless has been and where we're going and how this impending data revolution is going to happen. So this is an article that I was asked to write for IEEE Spectrum in August of this year. They asked me, what are the key things to 5G and where will we be for 6G? And so this came out on August 9th of 2021. And it turns out there are three fundamental technologies that are really starting to be deployed and understood. We're in the early days. 5G is in its early days. But around the world, engineers and technicians are starting to understand that three fundamental contributions are going to start exploding the data rate far beyond anything we ever envisioned. Those three key technologies are massive MIMO, which was really pioneered by my colleague, Tom Marzetta, who's now our director at NYU Wireless. He took it over for me a couple years ago. Massive MIMO, which is the idea of many antenna elements, hundreds of antenna elements at the base station. Millimeter waves, which is getting us wider channel bandwidth, wider bandwidth, and then the move to small cells. I want to make something clear about small cells. Small cells would be needed when you increase the channel bandwidth at any carrier frequency, sub 6 gigahertz or above 6 gigahertz. The basic theory of noise, FKTB, power of the noise is the noise figure times KTB. As B gets wider, noise power gets wider, so you have to move the transmission link closer to the receiver to overcome the thermal noise in wider bandwidth. That's at any carrier frequency, not just millimeter wave. But the fact is you have more spectrum available up at millimeter wave and terahertz and sub-terahertz. The channels are so much wider than what you can do at sub 6 gigahertz. So a channel bandwidth becomes much easier to find up at higher carrier frequency. So small cells, the small cell infrastructure, which is needed as we increase the channel bandwidth at any carrier frequency, is going to benefit millimeter wave and also sub-terahertz as we go there for 6G. Now, let me try to pull up this article because it's really worth reading. And I want to see if you can see my screen. I'm going to try to put this in and share my screen because I want to just scroll through a couple of things which are pretty fascinating. Let's see if this link will work. Here, I have it up. So let's see, where is that? I won't take a lot of time. It's the one thing about Zoom is it's tough to have another website up when you're doing this in real time. And I'm going to try to, well, you can read the article. It's pretty amazing. Basically, I take us through Cooper's Law. And by taking us through Cooper's Law, what I show is the industry has remarkably been close to Cooper's Law, but we're about to explode. We're about to go thousands of times higher in peak data rates than the 2 or 3 gigabit per second that we now enjoy in 5G millimeter wave. By the way, in the US, the 5G sub 6 gigahertz 5G new radio, they're operating speeds of about 400, 500, 700 megabits per second in the narrower bandwidth channels, concatenated 180 megahertz of spectrum channels down below 6 gigahertz. Getting up above 24 gigahertz in the US, we're seeing download speeds up to several gigabits per second, 3 gigabits per second, which is pretty amazing. But this article shows we're at the tip of the iceberg, and that while we consume today about 10 gigabytes of data per month on a smartphone, we're going to be consuming about a terabyte of data a day. A terabyte of data. We're going to go up to 100 times today's consumption in a smartphone. You say, what are we going to do with all that data? Well, historically, that's what has happened on the peak data rates. I show that in this article, and I show the evidence for why in 2031 we'll be at that kind of data consumption speed because of these three fundamental technology breakthroughs. Here's why we're going to have that data. This is an amazing point that I think you'll find astounding. This is what $1,000 buys, and we did this in our 2019 paper, Opportunities and Challenges, that 2019 100 gigahertz 6G paper. We laid this case out. If you look at what today's technology buys, we buy 10 to the 12th computations per second. We're able to get teraflops per second today for $1,000 in a high-priced smartphone. But by 2036, $1,000 will buy in a handheld package the computation capability of the human brain. This is why artificial intelligence and machine learning is generating so much interest and demand from the companies that are data mining. The Googles and the Facebooks of the world are basically doing the kind of algorithms and relying on that scaling of computational capability to get more and more computational capability that creeps towards the human brain. Now, human computation is not the same as human knowledge or cognition, but I use the term wireless cognition to define, we used that in the 2019 paper. Wireless cognition, I believe, will be the remoting of the human brain, remoting this kind of computational capability in real time. And I believe it will happen around the 2036 era. It'll lag maybe by a few years, just the way Cooper's law is lagging Moore's law on the growth and ascent of bandwidth. But look at this, it's not so far-fetched. Let's say we find a 10 gigahertz RF channel. Today, there are 200 megahertz channels in 5G in the US. 200 megahertz, 400 megahertz millimeter wave channels. Well, let's go to 10 gigahertz channels. That's only roughly an order of magnitude. Let's say we use 1024 QAM. We're already using more than that in 5G. We're using 4096 QAM. So we are already surpassing that by 2 bits per second. But let's do modest. Now let's say we can get 1,000 times the channel capacity. Now massive MIMO gives us about 10, as I show. We'll get to 10 to 20 in the next 10 years, as I show in that article for IEEE. Let's say there's another breakthrough that gets us from 20 to 1,000, so another factor of 50. And let's say we do all those three things, we can then carry a physical layer air interface real-time data rate of 100 terabytes per second. That gets us to about 1% of the real-time human brain computation. And if we do 100 gigahertz channels, that's 1 petabyte per second, or 5% of the human brain. In fact, how did I get that? It's just very simple air interface math. So we're going to be approaching in 15 years data rates that are approaching the real-time computation, and other breakthroughs from this conference and others may actually increase that. What do we do with that kind of human brain computation? Well, all kinds of applications. There's drones, autonomous cars, holographic sensing, detecting, see in the dark, all the applications we talked about in that 2019 paper. And it will happen. Now, in communications, you can imagine these kinds of data rates can start replace wiring. We can start doing backhaul, mobile, in-cell, Wi-Fi, in-band backhaul. So there are all kinds of great applications. And this is one of the amazing things I told you I wanted you to come away with. The whole world of wireless operated down here at sub 6 gigahertz for 40 years or more, where the attenuation in air and sea level is less than a fraction of a dB per kilometer. Less than a fraction of a dB per kilometer. And the 60 gigahertz unlicensed band was given away because it has such high attenuation, 20 dB per kilometer. Now, this is attenuation due to the molecules in air, water, vapor, oxygen, on top of the free space propagation laws. So this is additional attenuation above and beyond what you'd have in perfect free space with no atmospheric attenuation. So the whole world of wireless in the sub 6 gigahertz, 4G and before, had fractions of a dB. Well, look, other than the 60 gigahertz band, there's not that much attenuation. In fact, look at the blue at sea level, going all the way out to 400 gigahertz. If I go to 400 gigahertz, I only have 20 dB per kilometer, the same as at 60 gigahertz. If I go to 400 gigahertz, 20 dB per kilometer, with the move to small cells, getting cells to within every 100 meters, that's only 2 dB per 100 meters. So the truth is, going up in free space, in air, in a city with no obstructions, 400 gigahertz is only 2 dB more lossy than today's mobile. Yes, there are these resonance bands that you have to avoid, like 380 and 183 gigahertz, where you get huge attenuations. You know, this is getting close to 80 dB per kilometer. That's 8 dB per 100 meters. That's a lot, still viable. But you know, you get up here and there's hundreds of dB per kilometer. This is 700 dB per kilometer. That's 70 dB per 100 meters, that's 7 dB per 10 meters. So this would only be for very short range stuff on your body, near your body. And you go up to these frequencies, up at 600, 700, 800, 900 gigahertz rather, you have huge attenuations. But the amazing thing is the channel is not that lossy for a 100-meter small cell, even all the way out to 900 megahertz. All the way out to 900 megahertz, we're only 100 dB per kilometer loss, which is only 10 dB per 100 meters. 10 dB could be made up by 5 dB on each end of the antenna. And remember, the antennas are going to be physically small and have tremendous gain at these high frequencies. So you ask, well, what about rain? Well, rain, once you design the small cells for rain at 50 and 70 gigahertz, rain no longer matters because the wavelength is so small compared to a raindrop, and at flat tops, you have no more attenuation. So all the 5G cell sites being built out for millimeter wave will work. In fact, I'll show you, they're going to be more power efficient up above 50 gigahertz out to terahertz. So you can see on this graphic, we can go several kilometers with fixed point to point and mobile if we get antenna gains on the base station and the mobile. That's the key. We're transitioning from the omnidirectional world, how all the textbooks are written, to the directional world. In fact, this is how all textbooks up until our millimeter wave book were written. They considered omnidirectional free space, removing the antenna gains, omnidirectional zero gain. And yeah, this graph shows that you get more loss at higher frequency. That's how the world thinks today, but it's so wrong. It's totally wrong. The fact it's opposite. If you keep the physical area the same on each end of the link, you keep the physical area the same, what happens then is the higher frequency is actually stronger. You keep the same physical area of the antenna. An omnidirectional antenna means the antenna shrinks with wavelength. But if you keep the physical area the size, same size, steer the antenna on both ends of the links, you get more path received power at higher frequencies for the same physical antenna area. Now, yeah, it's true that you have obstacles like glass and drywall and trees and leaves are going to attenuate, but I'm going to show in a minute, things are also more reflective. So you're going to get energy where you didn't think you would in some cases. I'm going to show quick math. I won't go through it, but this is the fact that shows equation 3. Equation 3 shows that as distance is fixed, going up in frequency gives you a square increase. You get a square increase in power for given distance, going higher in frequency, if the air attenuation is not great. In fact, looking at it this way, if I have a carrier frequency at 3 gigahertz, the same physical size antenna, and this is what you have in a typical base station, typical mobile, physical areas. I have only a negative 90 dB signal. If I'm at 300 gigahertz, this is not including air loss. You could throw in a couple dB of air loss because it's a couple dB there. Negative 50 dB. I get 40 dB more signal to noise ratio going up to 300 than I do 3 if I keep the physical areas the same and steer the antennas at terahertz. And what do I do with that 40 dB of gain? I get 40 dB more signal to noise ratio, or I could use a 40 dB wider bandwidth channel. I can take in 40 dB more noise, so I can use a much, much wider channel and get the same signal to noise ratio, same bit error rate as I did at 3 gigahertz. It's so much more power efficient. I'm gonna go real quickly because I'm at the end of the time, but we've been measuring the channels, indoor, outdoor, indoor hotspots, UMI, and one of the key things we found in one of our early papers is if you use a 1 meter free space reference distance from all these measurements over 10 years, over all these spectrum, we just published them in the IEEE communications letters, just came out. If you use a 1 meter free space reference, the amazing thing is the path loss exponent reference to a 1 meter is remarkably frequency independent. It doesn't matter what carrier frequency, 28 to 140. You use a 1 meter free space reference list where it's that 1 meter where you go from near field to far field and you lose energy based on frequency. That's that omnidirectional formula we've used since Harold Freese developed it back 100 years ago. But in that first meter, if you reference every propagation measurement and every channel measurement around the world to 1 meter at any frequency, we're showing that all the way up to 140, we believe even higher, that you do that 1 meter, then you've got a channel model that can be used anywhere. And this shows that there's little less reflection at 142, but still there's viable multipath. Look, there's 2.5 on average different directions that energy is coming from in non-line of sight in New York City. And this doesn't even include diversity. Antenna diversity doubles this. And yes, the RMS delay spread decreases, but it decreases not terribly substantially. Indoor and line of sight, non-line of sight, we've got statistics now that show there's still diversity, still energy to exploit. And we've even gone outdoors. We've done the same thing. We're looking at the channels. And again, we did this during COVID. We've got some of the world's first data on urban microcell. It's amazing the results measuring the campus. And we find that these things are reflective, very reflective. They're attenuative when you're blocked. But this is looking at the channel at 1 meter, free space reference distance at 142. We're able to make non-line of sight links in deeply shadowed areas. And when you look at all the outdoor data, again, the same thing happens. Using a 1 meter free space path loss reference, non-line of sight and line of sight is virtually frequency independent because this term B in the frequency in the dependent frequency path loss model is close to 0. I won't do the details, but the good news is the channels are not that much different. They're a little tiny bit lossy due to the atmosphere, but that's really it. And there's a lot of energy, a lot of diversity. This is outdoor. Again, lots of multipath directions that you can exploit for communications. And again, multipath outdoors exists. And then you can start using MIMO. We just published this at GlobeCom this year. It's going to be presented how there's a trade-off on beamforming versus spatial multiplexing, but it works. You can make it work up to 142 gigahertz, and we believe much higher. And then finally, I'm going to end with this idea of co-sharing satellites and terrestrial networks. Right now, there are a lot of devices that work up above 100 gigahertz. They're up above the sky, but we can use this amazing attenuation of the atmosphere on long slant paths. If we can operate with keeping the energy on the horizon, we can share the spectrum and not interfere with these very sensitive weather satellites. That's a really fascinating area. This is where the ITU today has issued the spectrum. These are the unlicensed bands, but look at these bandwidths that are available up to 275 at the ITU. And we're gonna go much higher than that over the next decade. And we actually did some of the world's first measurements with the satellite way up on a building. It's a surrogate satellite, and we're looking down on the ground and trying to see how much energy bounces up from the ground, from the foliage. This was the only energy we could find in all the locations. We've just published this. It looks like it'll be pretty safe if we could keep that transmitter on the horizon. Here we're pointing up at about 30 degrees. So this is a busy graph, but you can find it in the paper. Once you do this, you can see you can get great positioning. We've done ray tracing. On a phone, if you could do real-time ray tracing, you can use the energy from the multipath with a map and find amazing position accuracy, whether you're in line of sight or not in line of sight, doesn't matter. The ray tracing can be done today on today's cell phone, real time. And what we did is we found that we could get very accurate location within a few centimeters in the NYU lab with only one base station. Look at this, 5 centimeter ranging out to 35 meters. And then we went outside, we found the same thing. If you could bring the map into the phone in real time and integrate position with the map of objects and where the multipath's coming from, you can get really good error, very low error within a half a meter. And we've even simulated it for drones. And we're doing it with AT&T and looking at vehicle navigation well within a meter at millimeter wave. So in conclusion, we've been working from 28, we're up to 140, we're gonna go higher. We've really tried to provide some foundational knowledge. It's a very exciting area for the future. We've seen enormous progress since we published that It Will Work paper about 5G. And we're going now above 100 gigahertz. And I hope you're convinced that there's clear sailing up to 900 gigahertz. We need to know the health effects. We need to make sure we protect those sensitive satellites up in space that have wide open receivers. But I think we can do it. With that, I'd like to thank you, Nobu-san, and wish you all a wonderful conference. And thanks to the many industrial affiliates who sponsor our work.
Thank you very much, Ted. Okay. I can have some 1 or 2 questions because we don't have much time for Q&A. Now I have one question from Professor Hadama. Please talk to directly to Ted. Okay.
Yeah.
Can you hear me?
Yeah, and I gave some.
Yes.
That's good.
Yes.
Thank you. Thank you for your very informative presentation. I'm very impressive. So my question is that is written in your final conclusion, but if possible, give us some comments on millimeter wave and human health.
Yes, I will. There was a wonderful session about this at the IMS. You should look it up. The 2021 IMS conference had a wonderful panel session. My colleague, Chris Collins from the med school was there. There is, and I mentioned it early in my talk, we looked throughout the literature in 2015 and we wrote a paper, Safe for Generations to Come. In fact, let me just remind you, I talked about it very early on. And there are no known health effects for millimeter wave. It's only due to heat. If you get so much energy that the skin starts to heat, then you have to worry about health effects, just like you get a burn. And this is the paper we showed it in. I'm going to show it right here. This is the paper. You can find this paper. This was basically a very, very thorough study before the world adopted millimeter wave and before I went to the FCC with the idea. We did this work. Now for sub-terahertz wave, when we get 1 order of magnitude closer to ionizing radiation, we believe there's some evidence that molecules vibrate, that the energy doesn't break the valence shell, but things can vibrate. And we need to understand how those vibrate and if they break apart and if there's problems. Up at 80 or 90 gigahertz in this paper, we saw that some things can vibrate, but they didn't ever break. You know, there's never any observations that at high power levels, very high power levels, they would not, right before they heated, they would vibrate. So the question is, we don't know up above the millimeter wave. We need to do that research. We need to understand what biologically happens. I wrote that in the 2019 paper. We need government funding around the world to study what happens up above 30, 50, 90, up above 100 gigahertz. You know, we have good evidence in this paper. We believe that things are safe below 80 or 90 gigahertz. We know that at 95 gigahertz, the water molecule, they're actually used by military weapons at 95 gigahertz to heat the body and cause discomfort for crowd control. But what happens above these frequencies for low-level radiation, we need to find out.
Okay, understand. Thank you very much.
You're welcome. Read this
Yep.
paper, though, for an understanding of the health effect issues. And also another paper we wrote at ICC that same year. We studied this very carefully and documented that.
Great. Thank you very much.
You're welcome. I'm
Thank you
sorry
very
I
much.
went over, Nobu-san. It's a
Yes.
great honor to be with you, and I wish you all a wonderful conference.
Thank you very much. Any other questions? Okay. I have one question
Yes.
about centimeter positioning. Centimeter positioning. I'm really interested in the locations or DOA estimation. Did you use the any special algorithms?
Yeah,
For,
and we published it. Yes, we've published it. We call it MAP-AT. We call it a map with multipath assisted positioning. And I'm going to show it to you right here. It's map assisted positioning with angle and time. So the idea is, if you have a transmitter with a known location and you have a receiver with an unknown location, all you know is there's a bunch of transmitters with known locations, known a priori, and you don't know where you are, but you know what you measure in angle and in time. And so what the receiver does, it exploits a knowledge of a map and figures all the possible ways that the energy it observed in angle and time could have reached it from a transmitter. And it basically sorts through, and we've documented the computational complexity. It's almost like a Viterbi algorithm when you try to figure out the best Viterbi code. You can figure out from the multipath received and its angle and its time delay, which walls it bounced from, and you can use many multipath to basically majority vote on where the unknown receiver location is based on the known transmitter location. So it's really exploiting the idea of having a map to do a ray trace for the multipath in angle and time. We filed a patent on it at NYU. It's shown amazing accuracy indoor and outdoor, and this is with only one base station. You start using 2 or 3 base stations, you can get even much more accuracy. So that's the ability to exploit the received energy, and you could put this on an overhead, an overhead signal on any air interface standard. So you're going to get position location for free when you don't have GPS or other things.
Thank you very much. I studied your MAP-AT in more detail. Thank you very much. Thank you. I'd like to close this keynote session by thanking Professor Rappaport and all the participants. Thank you very much. Thank you, Ted.
Thank you so much.
Thank you so much.